Grounding a water pump motor, particularly a sump pump, requires careful consideration, especially when the plumbing system incorporates plastic components. The primary objective of grounding is to provide a low-impedance path for fault current, thereby minimizing the risk of electrical shock and ensuring the reliable operation of overcurrent protective devices. In a residential setting where the plumbing is predominantly plastic, with only a short section of copper pipe near the valves, the standard method of bonding to the water pipe may not be adequate. Plastic plumbing is a nonconductive material, meaning it cannot serve as a reliable grounding electrode. Therefore, alternative grounding methods must be employed. One common approach involves installing a separate grounding conductor from the motor terminal grounding lug to a grounding electrode. This electrode can take several forms, such as a ground rod, a ground plate, or connection to the building's grounding electrode system. The National Electrical Code, or NEC, provides specific guidelines on grounding and bonding requirements. It's essential to consult the latest edition of the NEC and local amendments to ensure compliance with all applicable regulations. The size of the grounding conductor is determined by the size of the overcurrent protective device protecting the circuit. Table 250.122 in the NEC provides guidance on the minimum size of equipment grounding conductors for various circuit ratings. For instance, if the circuit is protected by a 20-amp breaker, an equipment grounding conductor of at least 12 American wire gauge copper is typically required. However, for a water pump motor, it is generally recommended to use an 8 American wire gauge copper conductor, as mentioned, to ensure a robust and reliable ground connection. This recommendation often stems from local jurisdictional requirements or best practices aimed at enhancing safety. When installing the separate grounding conductor, ensure it is properly connected to the motor's grounding lug and the chosen grounding electrode. The connection point should be clean and free of corrosion to minimize resistance. Use appropriate grounding connectors and follow the manufacturer's instructions for proper installation. If using a ground rod, it should be driven into the ground to a sufficient depth, typically at least 8 feet, and located where it is unlikely to be disturbed. The connection between the grounding conductor and the ground rod should be made with a listed grounding clamp or connector suitable for direct burial. Alternatively, if the building has a grounding electrode system, the separate grounding conductor can be connected to the main grounding busbar in the electrical pile. This busbar is typically connected to the building's grounding electrode system, providing a direct path to ground. Another consideration is the local authority having jurisdiction, or ODG requirements. Some AHJ may require an additional ground rod at the service when the plumbing is plastic, as mentioned. This is not uncommon in areas where the reliance on the plumbing system for grounding is deemed insufficient due to the widespread use of non-conductive materials. The additional ground rod provides an extra measure of safety by ensuring a low impedance path to ground. It is important to check with the local electrical inspector or building department to determine the specific grounding requirements in your area. They can provide guidance on the acceptable grounding methods and any local amendments to the NEC. In addition to the separate grounding conductor, it is also essential to ensure that the electrical circuit supplying the water pump motor is properly protected by a ground fault circuit interrupter, or GFCI. GFCIs are designed to detect even small amounts of current leakage to ground and quickly interrupt the circuit, reducing the risk of electrical shock. GFCIs are typically required in wet locations, such as basements or crawl spaces where sump pumps are commonly installed. The installation of a GFCI should be performed by a qualified electrician to ensure it is properly wired and functioning correctly. Regular testing of the GFCI is also recommended to verify its continued operation. Furthermore, it is crucial to maintain the integrity of the grounding system over time. Inspect the grounding connections periodically for any signs of corrosion or damage. Tighten any loose connections and replace any damaged components. If any electrical work is performed on the plumbing system or the electrical circuit, always verify that the grounding system is intact and functioning properly. The correct grounding of sump pumps is paramount due to the inherent risk of electrocution if the ground wire for the sump pump is connected to plastic plumbing. Plastic, being a non-conductive material, cannot provide a safe path for fault current, increasing the potential for electrical shock. In summary, when grounding a water pump motor in a residence with plastic plumbing, the following steps should be taken. Firstly, install a separate grounding conductor from the motor terminal grounding lug to a grounding electrode. Secondly, ensure the grounding conductor is sized appropriately, typically 8 American wire gauge copper. Thirdly, connect the grounding conductor to a ground rod or the building's grounding electrode system. Fourthly, check with the local AHA for any additional grounding requirements. Fifthly, install a GFCI to protect the circuit. Sixthly, regularly inspect and maintain the grounding system. By following these guidelines, you can ensure the safe and reliable operation of the water pump motor and minimize the risk of electrical hazards. It is always recommended to consult with a qualified electrician for any electrical work to ensure it is performed safely and in compliance with all applicable codes and regulations. Understanding the principles of grounding and bonding is crucial for electrical safety. Grounding provides a low impedance path for fault current, allowing overcurrent protective devices to quickly interrupt the circuit and prevent electrical shock. Bonding, on the other hand, connects all metallic parts of the electrical system together, creating an equipotential plane and minimizing voltage differences. In a properly grounded and bonded system, the risk of electrical shock is significantly reduced. The NEC provides comprehensive requirements for grounding and bonding in Chapter 250. This chapter covers various aspects of grounding and bonding, including the types of grounding systems, the size of grounding conductors, the methods of grounding electrodes, and the bonding of metallic components. It is essential for electricians and electrical contractors to be familiar with these requirements to ensure safe and compliant installations. In addition to the NEC, there may be local amendments or regulations that further specify the grounding and bonding requirements in a particular jurisdiction. These local requirements may be more stringent than the NEC and must be followed. It is important to check with the local electrical inspector or building department to determine the specific requirements in your area. Grounding electrodes play a critical role in the grounding system. They provide a connection to the earth, allowing fault current to safely dissipate. There are several types of grounding electrodes recognized by the NEC, including ground rods, ground plates, metal underground water pipes, and concrete encased electrodes, also known as grounds. Each type of grounding electrode has its own installation requirements and limitations. Ground rods are typically driven into the ground to a depth of at least 8 feet and should be located where they are unlikely to be disturbed. Ground plates are buried horizontally in the ground and should have a surface area of at least 2 square feet. Metal underground water pipes can be used as grounding electrodes if they are in direct contact with the earth for at least 10 feet. Concrete encased electrodes are steel reinforcing bars or rods that are encased in concrete and are typically used in new construction. The selection of the appropriate grounding electrode depends on the soil conditions, the available space, and the local requirements. In areas with high soil resistivity, multiple ground rods may be required to achieve the desired grounding resistance. The grounding resistance is a measure of the opposition to the flow of current from the grounding electrode to the earth. A low grounding resistance is desirable to ensure that fault current can quickly and safely dissipate. The NEC requires that the grounding resistance not exceed 25 ohms. If the grounding resistance exceeds 25 ohms, additional grounding electrodes must be installed until the resistance is reduced to an acceptable level. The grounding resistance can be measured using a ground resistance tester, which is a specialized instrument designed to measure the resistance of the earth. The tester applies a small current to the grounding electrode and measures the voltage drop to determine the resistance. The measurement should be taken under dry conditions to ensure accurate results. Bonding is another important aspect of electrical safety. Bonding connects all metallic parts of the electrical system together, creating an equipotential plane. This minimizes voltage differences between metallic parts, reducing the risk of electrical shock. Bonding conductors are typically sized according to Table 250.122 in the NEC. The size of the bonding conductor depends on the size of the overcurrent protective device protecting the circuit. Bonding conductors should be securely connected to the metallic parts using appropriate bonding connectors. The connection point should be clean and free of corrosion to minimize resistance. In addition to the grounding and bonding requirements, the NEC also provides requirements for the installation of overcurrent protective devices, such as circuit breakers and fuses. Overcurrent protective devices are designed to interrupt the circuit when the current exceeds a safe level, preventing damage to equipment and reducing the risk of fire. The size of the overcurrent protective device should be selected based on the ampacity of the conductors and the rating of the equipment being protected. It is important to follow the manufacturer's instructions when installing overcurrent protective devices to ensure they are properly functioning. Regular testing of overcurrent protective devices is also recommended to verify their continued operation. In summary, grounding and bonding are essential for electrical safety. They provide a low impedance path for fault current, minimize voltage differences between metallic parts, and allow overcurrent protective devices to quickly interrupt the circuit. The NEC provides comprehensive requirements for grounding and bonding, and it is important to follow these requirements to ensure safe and compliant installation. Local amendments or regulations may further specify the grounding and bonding requirements in a particular jurisdiction, and it is important to check with the local electrical inspector or building department to determine the specific requirements in your area.